Hey everyone, welcome back. So in the last video we left off talking about what pseudocode or an outline or sort of the planning stage would look like for implementing this encryption algorithm for the Caesar cipher. So just to come back from where we left off, this was the algorithm that I wrote out. Again, go through each letter in the plain text, calculate its position in the alphabet, add the key to this position, and then again somehow deal with this wraparound issue. Look up what letters at this new position in the alphabet, and then finally put this new letter into the ciphertext. And again, you would do all these steps for every single letter in the plain text. So what we're going to do now is we're going to continue on with sort of the stages of programming. So we've already done most of this first part here, this design and planning part, right? Writing out this algorithm, trying to figure out how it works. So now what we're going to do is we're going to take our plan, our algorithm, and basically go one step at a time and write out the code for it. Alright, so the first thing that we'll do is we're first going to make a global constant at the very beginning of our file that's going to define that alphabet that we work with. So again, a global constant is a variable whose value never changes, so these are okay to make in the global scope. You can make these outside of function definitions. For the purposes of these examples, we'll just use the standard A through Z English alphabet, all lowercase letters. Now, of course, you could edit this to change it to work with lowercase and uppercase letters. You would just, tack on all the uppercase letters after this, or maybe even before. But for most of the examples that we do, we'll just do all lowercase letters. So then, in our code, to sort of figure out, positions of where it is in the alphabet, we're going to refer to the positions of these letters in this string. So we've made this string, we've sorted into this variable called alphabet, this global constant. So whenever we're, trying to figure out where in the alphabet is a letter, we'll basically just look up its position or its index in this string. Alright, so one thing that we'll do is, looking at our algorithm, our sort of step-by-step outline, is one of the steps is put this new character into the ciphertext, right? So once we figure out what the encrypted version of the character is, we have to put it into the ciphertext. So what that means is we're going to have some variable that's basically keeping track of the ciphertext. At the beginning, that variable will have a value that's an empty string, right? Because at the very beginning, we have nothing in our ciphertext. Eventually, we'll build one string at a time into our ciphertext, but at the very beginning, we'll make an empty string like this. And again, be careful with your empty string notation. Make sure that it's completely empty, that there isn't even a space character in it, because a space is a character. So I'm naming this variable ciphertext because in this situation, we are encrypting something, so we're taking a plain text, which we're already going to have, and then we're going to build up a ciphertext one letter at a time. So the ciphertext is what we are creating. So we'll start off with an empty string into which we'll build the ciphertext. And then we talked about this we go through each letter in the plain text, right? And there's a lot of steps that we do for each letter, but as you can imagine, to go through each letter in the plain text, we're going to have to set it up with a for loop, right? And we talked about how with strings, which the plain text is going to be a string, you can iterate through every single character in the string by using a for loop. So you can do for variable in string, and that will iterate over every single character one at a time. So in this case, I'm using the loop variable letter just because we said we're going to go through each letter in the plain text, so it makes sense to name it letter. Of course, you could name this variable whatever you want, so long as you stay consistent with the rest of your program. And then we're going to go through everything in the plain text right now, because again, the plain text is what we already have. We are encrypting. We are taking the plain text, and we're going to build up the ciphertext. Alright, so again, just to sort of review, we have this global constant at the very beginning, this alphabet string, and then we do this for loop that we just talked about for each letter in the plain text, and then the first step that we do with each individual letter is we calculate its position in the alphabet. right? So again, we're going through each letter in the plain text. We do a couple steps to figure out the corresponding letter in the ciphertext. The first step that we're going to do for each letter is find its position in the alphabet. So conveniently, there is a built-in Python method that works on strings that basically returns the index of a character in a string, which is exactly what we want, right? So again, we're going through each letter in the plain text one at a time. And what we want to do is we want to find where that letter is in our alphabet, right? We want to figure out the index of the letter in our alphabet. So you can use this index method, and the way it works is you do alphabet.index, and then in parentheses, that's whatever character it's going to look for. And then the string that is before the period, in this case the alphabet, that's the bigger string that it's going to look inside of. So what this is going to do, this assignment statement right here, right-hand side, it's going to look up our alphabet, which is again that global constant, and then it's going to find the index of letter, whatever character that is, in alphabet. Once it finds that index, in this case it'll be anything between 0 and 25, right, because there's 26 letters. We start at 0, so 0, 1, 2, 3, all the way up to 25, which would be Z, and it basically returns that number. So what I'm doing on the left-hand side then, the variable that I'm making is letter position. Again, you can use whatever variable name you want. I just think that makes sense. If you want to spell out the entire word position, that's totally fine too. But again, this is just keeping track of, okay, now that we're going through each letter in the plain text one at a time, for each of those letters, so once we have one individual letter, what we'll do is we'll first find where it is in the alphabet, what position it's at, and then we store that position into this variable letter position. Alright, so then the next step is once we have this position, we have to add the key to the position, right? Because again, this is the shift cipher, the Caesar cipher. We're basically shifting over a couple of spots down the alphabet. So we already have, the letter position. We just got that by using this index method we just talked about. So then to get the new position, you can just take that letter position we just found and add the key to it, right? Now, we did have sort of a note to ourselves, right, that we had to deal with that wraparound issue that we talked about. Once we hit, the end of the alphabet, or the beginning, if we're going backwards, we have to, wrap back around that alphabet to continue shifting that direction. So we need to figure out a way to sort of deal with this wraparound issue in our code, right? Some sort of mathematical approach to deal with it. So to help us sort of figure it out, I've written out a couple of cases where, we do need a wraparound. So, for example, when the new position that we get is basically greater than or equal to 26, right? Because we already talked about how that last position in the alphabet, the character Z, is at position 25. So, if we get anything higher than 25, we need to wrap back around to the beginning, right? So, for example, 26 should wrap back to 0, right? So if we count past the Z, we need to wrap back around to the A. 27 should wrap to 1, 28 should wrap to 2, and so on. So again, we're trying to figure out how we're going to deal with this wraparound mathematically, how we're going to handle this in our code. So the tricky part of this is, on the previous slide, you might have thought, okay, well, if 26 needs to wrap to 0, why don't we just subtract 26, right? 27 has to wrap to 1, just subtract 26, right? That seems to work. The problem with that, though, is if we have a really big key, right, the key can be any integer, and, the key could be 100, it could be 1,000, it could be, whatever integer you'd like. So if you have a really big key, we might go beyond, just needing to subtract 26. So for example, if we get 52, we should also get 0. So 52 basically would wrap around the alphabet twice. 53 would also wrap around the alphabet twice and then move over 1, so that would wrap to 1. 54 would wrap to 2, and so on. So unfortunately, we can't just subtract 26 because it's very possible that when we add the key, that the key is big enough to give us a really big number. So we have to sort of do something mathematically that will always work. It will always, it will always sort of give us the remainder of doing a division by 26, essentially, right? Because we talked about how 26 should wrap around to 0, 27 should wrap around to 1, 52 should also wrap around to 0, and 52 divided by 26 divides evenly. 53 should wrap around to 1. If we divide 53 by 26, we'll have 1 left over. So this is essentially giving us, the result of the remainder of the division. So hopefully you can see where I'm going with this. So what we're going to do is we're going to make another global constant named alphabet size, basically, and that's going to be the length of the alphabet. Now, the length of the alphabet is 26. It's still good to use, LEN to get that rather than hard code in 26, just in case, later on you end up changing your alphabet for whatever reason. So then to calculate this new position, not only do we take, the previous letter position that we calculated using that index method and then add the key, but we also need to mod it by basically the size of the alphabet, by the length of the alphabet. Now this is doing that, that math calculation for us that I was just talking about. It's doing the division by 26, which is again the length of the alphabet here, alpha size, and then giving us the remainder of it. So this mod is really going to help us out. This mod basically allows us to wrap around the alphabet, or another way you can think of it is that it wraps around each time you subtract by 26. So that's essentially what the mod is, right? It tells you how many things are left over after you divide by 26. You can think of division as a repeated subtraction by 26. So every time we wrap, that's one more that we are able to divide with, and then anything that we have left over will be the remainder, and that will be the result of the mod. If you do have questions about how this mod works, you're still maybe a little bit unsure about it, please do let me know. But otherwise, we'll continue working on our code. Alright, so now that we have the new position, right, and again we're calculating the new position by taking the position of the original letter in the plain text, adding the key to it, and then modding it by the length of the alphabet. So this is how we calculate the new position of the character in the alphabet. Once you have that new position, you can then just say, okay, alphabet, tell me what letter is at this new position, right? And we talked about how you can do this using indexing, right? You have a string, like we do with alphabet, and we have an index, which new position is, right? New position is going to be some integer that we just calculated. To look up what character is at that position in our alphabet, we use the indexing operator. So the encrypted character, enc_char, the encrypted character is going to be the character at position, new position, in our alphabet. Alright, and then the last thing that we do with this is once we have the encrypted character from the previous line of code we just talked about, once we have this encrypted character, then put it into the ciphertext, right? Again, the goal of what we're doing here is basically we're going through each letter of the plain text, and for each letter of the plain text we have to do some math and, some string lookup stuff to determine what the new encrypted character is going to be. Once we have that new encrypted character, we'll take whatever ciphertext was before, because we're building up one character at a time. So we want to keep anything that was, in ciphertext before, because we're building it up, and then basically concatenate ciphertext with this new encrypted character. So then at the very end, you might have something that looks like this. Now, this is more of a sort of formal view of what the encryption function for a Caesar cipher might look like. We've talked about most of these lines already, but let's go ahead and run through it again just one more time just to make sure we're on the same page. So again, at the very beginning, we have our two global constants. This is our alphabet, and then also the size of our alphabet. And then if we want to put it into, say a function definition, and again, this time we're doing encryption. We're taking a plain text and a key, and we're giving a ciphertext back. So I went ahead and created a new function definition, named it ENC, basically short for encryption. It has two parameter variables, so key and plain text, because those are the things that we start with. As you can see at the very bottom, this is a value returning function, meaning when you call the function, it actually gives a value back to whatever part of the program called it. In this case, the value that it's going to return is the ciphertext, which makes sense because the whole point of encryption is to take the key and the plain text and basically give back the ciphertext. So then looking inside this function definition, first line of code is ciphertext gets this empty string. This is what we talked about earlier where, again, the goal is to build up the ciphertext one character at a time. So in order to, add more characters or concatenate more characters into ciphertext, you have to start it as a string. You have to start it as an empty string. So at the very beginning, we just say, hey Python, ciphertext is going to be a string. There's nothing in it yet, so give it this empty string right now. Then we hit our for loop, which basically says go through every single letter in the plain text. And then for each of those letters in the plain text, first find the position of the letter in the alphabet. That's what the letter position equals alphabet.index letter is doing. Next line of code, new position equals letter position plus key mod alpha size. That is the line of code that's saying, okay, now that I know where the original letter is in the alphabet, I'm going to go ahead and add the key. So this is essentially doing the shift for us. And then mod it by the length of the alphabet. And again, modding it by the length of the alphabet basically deals with any wraparounds that we have to do. So then at this point, the variable new position will have an integer, which is basically some number between 0 and 25 in this case. That basically tells us the position of the new character that we're determining, the encrypted version of the character. So then the next line of code, enc char, this is basically saying, okay, now that we have the new position, go ahead and look up in our alphabet whatever character is at that new position, and then give me that character back. So enc char, this will be a string. Specifically, it'll be one character from our alphabet. And then the very last line of code we have in our for loop is once we have that new character, go ahead and put it into ciphertext, right? So again, the goal with this for loop here is we're going through each letter in the plain text, doing some string lookup, some math, more string lookup again. Then once we figure out what the new character is, what the encrypted character is, then put that encrypted character into the ciphertext. So we're building up the ciphertext one character at a time as we go through this for loop. At the very end of the for loop, we will have iterated through the entire plain text, meaning we will have gone through every single letter in the plain text, and we will have built up the ciphertext. So at that point in time, we'll have the entire ciphertext. So then, finally, we can just return ciphertext, because again, that's kind of the whole point of this function, is to figure out what the ciphertext is, and to give it back to whatever part of the program called our function in the first place. So that code that I just posted, the encryption function, that code is available on Canvas for download. So if you want to download it and run it a couple times, test it, see how it works, you're more than welcome to. But for example, this function call, enc5, north, will return the following string. So because it's a value returning function, if you just run with this function call, it's not actually going to display anything because it's just returning a value. So if you wanted to actually display something, you could put print around this function call here. So you could do print parentheses enc parentheses 5 comma north parentheses parentheses if you wanted to actually see the result. Again, that's because this is a value returning function. It just returns a value. So again, this is the same example that we did earlier, right, when we were first talking about how the Caesar cipher worked, where I said, okay, what is the encryption of north with the key 5, right? And you already worked through this by hand, and this is what we got. And our code will give us the exact same string. So again, you're more than welcome to run that and test it. Make sure you get the same thing back. If you have any questions about running it, please do let me know. Alright, so the thing about ciphers is generally when you write code for ciphers, you need to write both algorithms, meaning there's an encryption algorithm, which basically does the encryption, right? It takes the plain text, gives you ciphertext back. You should also write the decryption code, meaning you should also write code that basically does the opposite direction, where you start with the ciphertext, meaning you start with the jumbled up version, and then you go backwards and give us the plain text version back. So whenever you're doing this cryptography stuff, generally you will be writing 2 functions at a time, one for encryption, one for decryption. The nice thing about decryption, though, is that the algorithm for it is almost identical to whatever the encryption algorithm is, which makes sense because you're doing the same thing just backwards. So the differences are you start now with the ciphertext and then you return the plain text, right? Because that's the whole point of decryption. With decryption, you already have the ciphertext. You already have the jumbled up version, and you're going to give back the plain text version. Versus encryption, you start with the plain text and then give back the ciphertext. The other difference is you're going to reverse the math. So whatever math you do to calculate, the new letter, that math is just going to be reversed. It's going to go the other direction. So, keeping those differences in mind, this is what the function for decryption is going to look like. And I've put in bold the differences between this function and the encryption function that we just talked about. So obviously the name of the function is going to be different. And then the 2 parameter variables, you'll still have a key, but this time you'll have the ciphertext as a parameter variable instead of the plain text, because again, we start with the ciphertext, and then as you can see at the bottom here at the very end, we'll return the plain text. So again, the idea here is that we're going to go through each letter in the ciphertext, and as we're doing that, we're going to determine the new letter in the plain text. So we start with plain text being empty, because that's what we're building up. Whenever we do the math, which is what we're doing on this new position line, whenever we do the math, we're just going to reverse the math from encryption. So with encryption, we did, letter position plus key mod alpha size. The reverse of that is basically just, instead of addition, you do subtraction, right? That's the reverse of addition. You just do subtraction. It's the opposite. So in this case with decryption, you'll take letter position, subtract the key, right? That's basically going backwards in our shift. And then you'll still do this mod, just in case you have wraparound stuff. And then again, we're now calculating basically the decrypted character, not the encrypted character, right? Because we're starting with the encrypted version, the ciphertext, and we're trying to decrypt it. We're trying to figure out the plain text. So we're building up the plain text 1 character at a time, and then eventually returning the plain text. So again, good news about any of this crypto stuff that we're talking about. Once you write the code for the encryption function, the code for the decryption function, you can kind of just copy and paste it and then change a couple variable names and then change the math. That's it. But once you have encryption working, you won't be too far away from working out your decryption. So just like I have posted the code for the encryption function for the Caesar cipher on Canvas, I also have posted the code for the complementary decryption function. So again, these are complementary functions, meaning, in that previous example we saw, when we encrypted north with the key 5 and we got the string STWYM back, you should then be able to take that string that we got back, STWYM, put that into our decryption function with the same key, 5, and then that will give us the original plaintext message, which was north. So you can always, sort of test to make sure that your functions are working by calling, the complementary function with the result to make sure you're still getting the same thing back. That's another nice thing about this crypto stuff. But again, you can go ahead and test this with the code that I've posted. And again, if you have any questions while you're running that code, please let me know.